Hello everybody! In this video, we're going to learn about equations of lines. And I know what you might be thinking. You've already learned about equations of lines in an algebra class years ago. But in this video, I'm going to show you a cool new way to write down the equation of a line. A way which is easy for 2 dimensions and also generalizes to the 3-dimensional case. Now, the equations of lines you may have seen before are in a form that's called implicit form. Y implicitly depends on x. That means given any x value, you would then find a value for y. Maybe you've seen equations of lines written in the form y equals mx plus b, where m is the slope and b is the y-intercept. Or maybe you've even seen them written in standard form, a times x plus b times y equals c. And those are okay forms for the equation of a line. But I'm going to show you parametric form. A parametric form means that both x and y will depend on an independent third variable called t. And t is sometimes called the parameter or the free variable in this kind of an equation. So here's the way it works. Given 2 points, let's call them P and Q, 2 points on a line L. I'll usually write my lines with script letters. First, calculate the vector m between those 2 points. Just as we've done before, the vector from P to Q you can calculate as Q minus P. And then the parametric equation of a line have this form. L of t, so I'm writing it as a function, L of t is equal to vector m times t plus your point P. And in this equation, we think of the vector m as the slope vector, shows you the direction or the slope along this line from the point P to Q, and think of t as your base point. It's kind of like your starting point on the line. So it's kind of similar to y equals mx plus b, except instead of a single number representing slope, you have a slope vector. Instead of having a y-intercept, which is really just a point on the y-axis, you have p, which is a base point. It can really be any point on the line. There's no reason to restrict yourself to the y-axis. So again, this form is called parametric form for the equation of a line. Again, it kind of looks like a function, and for any value of t, you'll get a point on this line. And you plug in a value for t, you're going to do a scalar multiplication and then some vector addition, and the result will be some point along this line, as we'll see in the next example. So, for example, let's say you have the point 1, 3 and the point 3, 7. We want to calculate the parametric vector form of the equation that is the line between these 2 points. Well, first, we calculate the slope vector. So q minus p. 3 minus 1 is 2, and 7 minus 3 is 4, so our slope vector is 2, 4. The equation of this line, L of t, which is m times t plus p, that's our slope vector, 2, 4 times t plus 1, 3. To get points on this line, we just plug in values for t. So for example, if we calculate L of 0, put in 0 for t, so you have 2, 4 times 0, that gives you 0, 0, plus 1, 3. 0, 0 plus 1, 3 is 1, 3. Right, so that gives you actually your original point P. It's kind of why we call P the base point. Then L of 1, right, to calculate this, you would plug in 1 for t. So you'd have the vector 2, 4 times 1. That's the vector 2, 4. 2, 4 plus 1, 3 is 3, 7. Right, and that actually is our point Q. Right, so when t equals 1, you get this point on the line. Then you can plug in other values other than 0 or 1, and they'll give you different points on the line. In general, when you write the equation of a line in this form, L of 0 will always give you P, and L of 1 will always give you Q. But let's say, for instance, L of 1/2. Right? So if you plug 1/2 in for T, 2, 4 times 1/2 is 1, 2. And the vector 1, 2 plus 1, 3, that's 2, 5. Right? And that point actually lies halfway between P and Q. Right? In fact, if you plug in numbers between 0 and 1, you'll get the points between P and Q. Math works out nice like that. You can kind of think of T as time. Right? At time t equals 0, you start at P. At time t equals 1, now imagine yourself moving along this line. When t equals 1, you're at Q. And times in between those, well, you'll be in between those 2 points. When t equals 2, that moves us a little bit further down the line. To calculate that point, we'll plug in 2 for t. So 2, 4 times 2 gives you the vector 4, 8. The vector 4, 8 plus 1, 3 gives you 5, 11. So that would be this point over here, point 5, 11. And even if you think of t as time, you can think of negative time as traveling backwards along this line. So what about when t equals negative 1? Be on this side of the line. Plugging in negative 1 for t, you'll get the vector 2, 4 times negative 1. It gives you negative 2, negative 4. The vector negative 2, negative 4 plus 1, 3 yields negative 1, negative 1. That's the coordinates of this point right here. And that's all there is to it. That's how you calculate the parametric form of the equation of a line. Parametric vector form. It uses vectors, which are pretty useful. Now, there's other ways you could write this as well. So, for example, you could take this expression and you could actually do the scalar multiplication here. So you could multiply 2, 4 by t and get 2t, 4t. And then you could do the addition. You could add 1, 3 to that to get 2t plus 1 as the first component, and 4t plus 3 as the second component. And the first component, that's your x, and the second component, that's your y. So, if you wish, you could take this parametric vector-based form, and you could rewrite it as a pair of equations, one for x, one for y, both in terms of t. That's also fine. Let's do one more example, and once you get used to this, it's pretty quick to calculate the parametric vector form. Let's say you want the vector, you want the parametric equation between the point 5, 3 and 1, 10. The first thing we need is the slope of the vector, or the slope vector from p to q. So you can calculate it as q minus p. Right, so 1 minus 5 is negative 4. 10 minus 3 is 7. Your slope vector is negative 4, 7. So the equation of your line, L of t, is the vector negative 4, 7 times t plus 5, 3, your base point. That's it. Now, if you wish, these two concepts are completely equivalent. It's possible to go back and forth. If you start out with parametric form, you can convert that to implicit form. If you start with implicit form, you can convert that to parametric form. And here's how you would do it. It's just some algebra here. So, let's say you start off with a parametric form of the equation of a line. So L of t is vector 2, 3 times t plus 1, 4. Well, first, separate that out into two equations, as we saw in the previous slide. Right? The x is the first components, so x is 2 times t plus 1. The y, the second component, is 3 times t plus 4. Right? So convert your parametric equation into two equations for x and y, and then take the x equation and solve that for t. In this case, we would move the 1 to the left side and it becomes minus 1. Then you'd multiply both sides by a half to solve for t. When you do that, you get t equals 1/2 times the quantity x minus 1. And now, since you know what t is, you could actually plug that into the equation containing a y. This is sometimes called eliminating the parameter. Right? So substitute that in. So y equals 3t plus 4 becomes y equals 3 times 1/2 times the quantity x minus 1 plus 4. If you expand that all out and combine your constants, you'll see that this gives you the implicit equation y equals 3/2 x plus 5/2. Me, I prefer the whole number form myself. Similarly, if you have an equation in implicit form, and you've just decided that you really like parametric form, here's how you convert it. There's lots of ways you can convert it. One way would be, say, let x equal t. And then we're going to write x equals t. We'll write that in the strange but useful form 1 times t plus 0. Still t, but it's in the form 1 times t plus 0. And then, if x is equal to t, then we could rewrite the y expression as y equals 3t plus 7. Now both x and y have the form of a number times t plus a number. And so we kind of do the reverse, what we did before. We'll take these two equations for x and y in terms of t. The coefficients of t, that's our slope vector, 1, 3. The constant values we're adding in, those are the components of our base point, 0, 7. So there you go. This turns an implicit equation into a parametric equation. And in general, it's going to follow the same pattern. If you have an equation that looks like y equals mx plus b, your equation's always going to look like this. Right? In this case, the slope vector would be 1, m times t, and the base point would be 0, b. Now, as a side note, there are lots of equations that look different but are actually the same. Right? You don't have to use this as a base point. You can pick any point along the line to serve as your base point. Similarly, any constant multiple of a slope vector is still a slope vector. Right? So parametric form has lots of equivalent ways to be written. Now, there's some nice advantages to parametric form. For instance, if you're used to y equals mx plus b, maybe at some point you encountered a vertical line, a line that goes straight up. What's the slope of that line? That would involve dividing by 0, and as we know, that's mathematically impossible. You cannot divide, say, 1 by 0. That calculation makes no sense. Right? So how do you write the equation of a line like that in y equals mx plus b form? Well, you really can't, right? A vertical line would be something like, x equals 3, right? It's a special case. Or you might instead use standard implicit form. But you know what? Parametric form is okay with vertical lines, right? If you have a line which is going straight up, your slope vector is going to be 0, 1. That's it. So it handles vertical lines very nicely, but much more importantly, since this is multivariable math, like 3D math, this process, coming up with an equation of a line, it generalizes perfectly nicely to 3 dimensions. It's exactly the same calculation, except our vectors and our points have a third component. If you tried to write an implicit form equation of a line, that actually is a lot more complicated. You'd have to write y in terms of x and also z in terms of x. I'm not even going to talk about that. That's more confusing than we need. So as an example of how you'd calculate the equation of a line in 3 dimensions, using parametric form, of course, let's say someone gives you 2 points. Right? So P is the point 1, 3, 8, and Q is the point 3, 7, 5. Right? Your first step is to calculate the slope vector. Right? In this case, that vector m is Q minus P. So 3 minus 1 is 2. 7 minus 3 is 4. 5 minus 8 is negative 3. There's your slope vector. And the equation of the line is still slope vector times t plus base point. In this case, 2, 4, negative 3 times t plus the point 1, 3, 8. That's it. To come up with points on the line, well, you do the same thing as before. You can plug in values for t. If you plug in t equals 0, you should get p. If you plug in t equals 1, you should get q. And any other value will give you another point on that line. The kinds of problems we'll often see, usually we think of a line as being defined by 2 points. So you can expect to say, be given 2 points, and you should be able to find the equation of the line containing those points. But you should also be able to find other points on that line. So, as one final calculation example, with these 2 points, let's first calculate the slope vector. Right, so that'll be, I'll use the second point minus the first. So 2 minus 1 is 1. 2 minus 2 is 0. 5 minus 3 is 2. So that's the slope vector. You could have done the points in the opposite order as well, and you would still get an equally valid answer. So, to calculate the equation of the line, right, it's the slope vector times t plus your base point. Again, you could use either point as the base point. I'm using the one with the smaller numbers, because that's going to make calculations a little bit easier. Now, to calculate 2 other points on the line, you're going to want to plug in values for t other than 0 and 1. So I'll pick 2 nice whole numbers, L of 2. Right, so I multiply the vector, the slope, by 2. We'll get 2, 0, 4, plus the base point, 1, 2, 3. Get 2 plus 1 is 3. 0 plus 2 is 2. 4 plus 3 is 7. So there's another point on the line, 3, 2, 7. One more time, just for good measure, let's let t equal 3. The slope times 3 is 3, 0, 6. Plus the base point, 1, 2, 3. 3 plus 1 is 4. 0 plus 2 is 2. 6 plus 3 is 9. So there we go, a second point on that line. And there you have it. That's how you can calculate the equation of a line between 2 points in either 2 or 3 dimensions using parametric form. Thanks for watching.